Hey everyone, and welcome to This Explainer. Today, we are taking a deep dive right into the building blocks of cloud engineering. Because let's face it, the cloud is definitely no longer just a corporate buzzword. It is essentially this massive, global toolkit that every single modern engineer absolutely has to master. So whether you're looking to wrap your head around core service models like IaaS, PaaS, and SaaS, or you want to decode some of those highly complex deployment architectures, you are in the exact right place. We're going to unpack the fundamental skills you actually need to build the modern internet.
Okay, let's dive right into this. Here's our roadmap for today. We'll start with defining the cloud, move into the three service models, then exploring deployment architectures, followed by cloud networking, cloud costs and FinOps, and finally, we'll wrap up with the future cloud engineer.
Section 1, defining the cloud and taking a quick look at where it all started.
It's honestly wild to think about how incredibly fast we went from massive room-sized mainframes running on reels of magnetic tape in the 1960s to the massive commercial explosion we're seeing today. I mean, it all kicked off back in 1963 when DARPA funded MIT to develop a really primitive cloud system just so a single computer could be used by multiple people at the same time. Fast forward a bit to 1969, and JCR Licklider helps develop ARPANET, pushing this brilliant vision of what he called an intergalactic computer network. Then, in 1997, Ramnath Chelappa actually defines the modern paradigm, accurately predicting it would be entirely driven by economic rationale. Just 2 years after that, Salesforce pioneered delivering software directly over the internet. And then, 2006 hits, Amazon Web Services officially launches, and the game was completely changed forever.
So what is the cloud, officially? Well, the National Institute of Standards and Technology, or NIST, defines it by two absolutely crucial characteristics: on-demand network access and a shared pool of resources. Basically, it means you can unilaterally provision computing power, like server time or network storage, completely automatically, without ever needing human interaction from the provider's side. You get this rapid provisioning with barely any management effort.
Moving on to Section 2, the three service models. Basically, the core building blocks of the cloud. And this brilliantly illustrates how cloud architecture is essentially tiered based on the level of control you, as the user, actually want. Down at the base level, we have IaaS, or Infrastructure as a Service. This is your raw, virtualized infrastructure, the servers, the networks, the storage. You have a really high management load here, meaning you're the one handling the operating systems and firewalls. Now, if you step up a tier to PaaS, Platform as a Service, you're getting a fully baked development platform. The provider handles all the tricky underlying infrastructure, and your team just gets to focus on hosting and deploying the actual applications. Finally, all the way at the top is SaaS, Software as a Service. These are your ready-to-use apps where the provider runs the whole show, and you're just tweaking basic user settings.
To make those abstract models a bit more concrete, think about the tools we see every day. For IaaS, we're talking about the absolute titans: AWS, Microsoft Azure, and Google Cloud Platform. Now, if you're a developer jumping into PaaS, you're probably looking at tools like AWS Elastic Beanstalk or Google App Engine. And for SaaS, well, that's the stuff we literally all use: Google Drive, Salesforce, Microsoft 365. You just open a web browser and you're good to go.
Section 3, exploring deployment architectures. Let's talk about how these systems actually get deployed.
When companies set this stuff up, it really boils down to two major strategies: hybrid cloud and multi-cloud. A hybrid cloud merges private and public clouds together. It's an incredible setup if you need to integrate older, legacy systems while keeping high security, but, and it's a big but, it can be wildly complex to manage and shuttle workloads back and forth. On the flip side, you have a multi-cloud strategy, which means using multiple public clouds simultaneously. Think running AWS and Azure at the exact same time. The massive win here is that it completely eliminates single vendor dependency and massively boosts your overall resilience.
Modern IT strategy is perfectly summed up by this quote: "The real question today isn't whether to go cloud, it's how to intelligently combine hybrid and multi-cloud to slash costs, accelerate innovation, eliminate vendor lock-in risks, and ensure zero downtime resilience." It's no longer an all-or-nothing game. It's entirely about making really smart combinations.
And the data totally backs this up. A striking 87% of enterprises are already operating in a multi-cloud environment today. Think about that. That means if you're an aspiring cloud engineer, having cross-platform knowledge isn't some fancy luxury on your resume anymore. It is an absolute baseline essential. Moving right along to Section 4, foundational cloud networking. The gritty, day-to-day skills you need. Now pause and think about this for just a second. With all this data constantly bouncing around the globe, distributed across dozens of different vendors and data centers, how does data actually find its exact destination?
It is quite literally the most fundamental question of the internet, and the unseen mechanics behind it are just fascinating.
It all comes down to the IP protocol. It's really kind of like the global postal system. Because IP is a connectionless network layer protocol, every single packet of data has to be stamped with a network identifier and a host identifier. The network portion acts like the street name. It routes the packet to the correct overarching subnetwork. Then, the host portion acts like the specific house number, ensuring the data hits the exact target node within that network.
If we're talking about IPv4, that address is built on exactly 32 bits, which are broken down into 4 numbers called octets. Those 32 bits form the absolute bedrock of subnetting. They dictate exactly how engineers chop up and design their virtual private clouds, or VPCs, to keep things highly efficient and incredibly secure.
Now, what's really interesting about this is how much we've had to evolve. Early on, IP relied on a rigid class-full architecture, classes A, B, and C. But man, was it inefficient. Imagine a company just needing 2 IP addresses for a simple point-to-point link. Under that old system, the smallest block they could be assigned was a Class C network, which gave them 256 hosts. What a massive waste of addresses, right? That glaring limitation is exactly what forced the industry to develop CIDR, which is classless interdomain routing, and VLSM, variable length subnet masking. These modern techniques let engineers create subnets of all different sizes, which conserves IP addresses and drastically cuts down on network traffic.
Section 5. Cloud Costs and FinOps. Basically, the harsh reality of paying for all of this. Look at this number, because it is staggering. Cloud spending across the industry is jumping up by over 64% annually. Because costs are spiraling upward that fast, cost optimization isn't just a clever accounting trick anymore. It is a literal survival skill for modern engineering teams.
To keep things from totally going off the rails, organizations are building these cross-functional cloud center of excellence teams. And they rely on holistic frameworks, like the AWS well-architected framework, to guide them. They aren't just blindly checking boxes. These teams have to constantly balance 6 core pillars. They need operational excellence and ironclad security, all while delivering zero downtime reliability. At the exact same time, they have to ensure performance efficiency scales up perfectly, forcefully drive cost optimization, and keep an eye on long-term sustainability. Honestly, it is a non-stop strategic balancing act.
And finally, Section 6, the future cloud engineer. Let's look at what is coming next. The literature is pretty clear on the massive challenges the next generation of engineers, maybe you, will be hired to solve. You're going to be tasked with integrating incredibly heavy AI and machine learning workloads. You'll have to expertly navigate the gray areas of shared security responsibilities between your company and the cloud providers. You'll be dealing with complex data sovereignty laws to make sure you stay compliant as data jumps across international borders. And, as we touched on earlier, you'll be constantly working to prevent vendor lock-in by designing those highly resilient multi-cloud setups. Of course, the absolute biggest disruptor in the room right now is generative AI. According to industry research, AI-driven cloud services and edge computing are fundamentally revolutionizing infrastructure from the ground up. These technologies demand scalable processing of truly massive data sets, which just means future engineers are going to have to architect even better, infinitely more flexible systems to handle the load.
So I'll leave you with this one final thought. As cloud computing continues to completely reshape the entire global economy, giving us instant access to shared resources and basically fueling the AI revolution, are you ready to architect the future? The tools and concepts we covered today, they are just the very beginning of that journey. Thank you so much for joining me on this explainer, and I really hope this sparked your curiosity to dive even deeper into the incredible world of cloud engineering.